This is the fifth class of this week. Let us continue with what we have been doing from the last couple of classes. See, if you recall, in the last class we rewrote all the governing equations for elasticity in terms of complex variables, and if you recall, these were the equations. The stresses were gamma z and psi z, they are Km potential. So, gamma x plus gamma y is equal to this, and gamma y minus gamma x plus 2 I sigma x y is equal to this. Now, again you recall, we discussed also in the last class why this particular form is written, because if you write this particular form, then essentially you have three conditions you can derive from this, the first two equation. If you compare the real part in the first equation, that gives you gamma x plus sigma y, and then in the second equation, if you compare the real part, it gives you sigma y minus sigma x, and if you compare the imaginary part, this is sigma x y. So, essentially these are three equations, though it is written in complex variable form, it is two equation. Similarly, the same thing you can write in polar coordinate system. The first one, these and these are the same equation, and then you can do you can write the displacements are also in terms of their in terms of complex variable representation. Now, this was the equation, stress equation, and then similarly we can have the equation for displacement. This is essentially the Navier's equation, and these equations, when written in terms of these Km potentials, then this equation gives you that. We also discussed then how to, through one example, what is the use of these equations, both the equations, the stress equation and also the displacement equation. And the general procedure is like this. We have to assume one potential, here in this case two potential. If you recall, when we solve these problems in Cartesian coordinate systems, we started with an assumption of Airy-Stress function. Now, here the Airy-Stress functions now is represented in terms of two potential, one is gamma and another is psi. So, we have to start with, if you any problem in elasticity that we need to solve using complex variable method, once the problem is described means all the equations are written and the boundary conditions are specified. Then when you start solving it, the first step would be to have an assumption of these potentials gamma z and psi z. Once you have that potential, then we have to substitute this potential in these equations, the stress equation and the displacement equation, then compare the real part and the imaginary part, we get the set of equation in terms of constant, and then we apply the boundary conditions to get those constants. That is the general procedure, and that's we demonstrated in the last class through a very simple example. Okay. Now, one thing we did not discuss in the last class, that is the boundary condition. See, if you recall, the boundary condition can be of two types. One is the traction boundary condition, where the stresses are specified at the boundary, traction is specified at the boundary, not the stresses. And then another boundary condition is the displacement boundary condition, where the displacements are specified at the boundary. Now, like we write the displacement in terms of we write that displacement u is equal to u x plus I u y, or in polar coordinate system, if you can write u is equal to u r plus I u theta. So, similarly, the traction also can be written in terms of this complex variable. Now, suppose we have take any arbitrary domain, and suppose A B is the boundary where the traction is specified, and suppose the traction, the component of the traction is in x direction is T x, and then component of traction in y direction is T n, and n, if you recall, n is essentially because this surface at this point, this is the outward normal. So, this surface is represented by, at this point, the tangent to this surface is represented by this outward normal, and that's why this n is written here. So, it is essentially traction on a plane which is specified by this which is represented by this normal vector small n. Okay. So, if this is the traction, then similar to your stresses, displacement, everything, the traction can also be represented as, say, total traction is equal to Tx, which is total traction in n on that plane is equal to I into Tyn. Okay. Now, recall we also know that traction is equal to the relation between traction and the stress at a given point, that is equal to sigma dot n. The sigma is the second order tensor, stress tensor, and n is this outward normal. So, if n is equal to say nx and ny, which are the components of n, and sigma is equal to, if you recall, sigma xx, sigma xy, and then sigma xy, sigma yy. So, this essentially gives you that Tx is equal to, this gives you sigma xx nx plus sigma xy ny, and similarly Ty in that becomes sigma xy ny plus sigma yy ny. This is nx. Okay. So, this is the traction that we know already. Now, sigma xx and sigma xy and sigma yy can be represented in terms of the Airy-Stress function. Again, Airy-Stress function can be represented in terms of this potential, if you recall. Now, if we substitute that potential in this expression, and then the final expression would be, final expression for traction would be something like this. This final expression for traction will be something like this. Okay. Now, this is the final expression for traction. This is the final expression for traction. Now, just to give you an example, suppose you take this example. Suppose this is the equation given. Okay. Now, if we have suppose we have something like this, look at the conditions given here. Suppose this value is p, and suppose this is a, okay, or take, say, unit value. Suppose this is unit, this is, say, 1, okay, or a, suppose a. Okay. So, what are the conditions we have? Now, conditions we have: sigma r is equal to p, sigma r at r is equal to a is equal to p, and sigma theta theta at sigma r theta at r is equal to sigma theta r, or r theta r is equal to a is equal to 0, right. Now, then your stress tensor becomes sigma stress, or at this point your stress tensor become sigma r is equal to p, sigma r theta is equal to 0, and sigma theta theta is equal to 0. Now, similarly, if you substitute that on that any plane, your traction would be, then you can calculate T is equal to the sigma dot n. N would be the any outward normal vector here, and then if we substitute this, your final traction will be Tx I plus I into Ty. Okay. This will be the traction on the entire plane. Okay. This we can write in terms of polar coordinate as well. If you write this, if you use sigma r and sigma theta theta, then you can write the entire expression in terms of polar coordinate. Okay. Well, when we solve an example, probably this representation will be more clear. Now, let us move on for the time being. Now, similar to traction, like that what we have here, we can also define the forces. For instance, suppose we have we know the, take this example. Okay. Suppose the forces, similarly total force will be, how do we get the force? If this traction at every point is, if it is integrated over the entire surface, then we can get the force. For instance, the force will be total force, which can also be written in terms of Fx plus I into Fy. So, that will be the integration of total traction, that integration over A to integration over the entire domain, right, this and then ds. And this will be, you have traction is equal to this will be T x n plus T y n I into T y n, and this integration of ds over A to B. Now, look at this expression is this, and this can be written as, so this minus I will come here, minus I, and then A to B, and this entire thing becomes d of the gamma z, and then plus z gamma dash z conjugate plus psi z, again its conjugate, d of this, and this essentially becomes gamma z plus z gamma dash z plus psi z gamma z. This is evaluated at A and B. This expression is important because both the expression, this expression and this expression, because sometimes what happens, sometimes the boundary conditions are given in terms of forces. In that case, we have to express the force like this. Okay. Similarly, sometimes you can have boundary condition given in terms of say moments, and in that case how do we write those boundary conditions? Suppose the moments is equal to, if you write moment is equal to the force multiplied by the distance. So, integration of T x, which is this x into T x plus then I into you get this thing, that T y, which is n into y, that integration over ds. So, this if you can substitute, you get the corresponding expression for moment, right. So, this is important because as I said just now, sometime for we may encounter different problems where the boundary conditions are given either in terms of traction or the boundary condition given in terms of forces or moment. So, how to take those forces and moments, how to represent them in terms of complex variable, this is an example of that. Okay. So, let us move on. Now, you see, so one thing is, see, if you look at the procedure, the procedure is, there is nothing new in the procedure, just I have mentioned that many times, the procedure remains same. Only problem, the only thing which is important here, and the previous methods, the Aristotle's function methods also, that we have to start with an assumption of gamma z. We have to, in this case, gamma z and psi z. Once we have some assumption, once we start with some assumption, rest of the thing is you substitute that expression of gamma z, the potential in the governing equations and the boundary conditions, and then find out the associated constant. Now, but the only thing is here, when we solve this purely we wrote this in terms of x and y and phi, the Aristotle's function, then it was just the one function, the phi we had to choose. Now, in this case, the Aristotle's functions are written, function is written in terms of two potentials. So, we have to assume two potentials. Now, you see, now these assumptions are not very straightforward, unlike phi. You see, there are three different kinds of domain is given here. One is the simply connected domain. We already discussed what is simply connected domain, and another thing is domain is finite domain. It has a finite boundary. Then the second one is a finite boundary domain, and then it is a multiply connected domain. You have these are internal, these are some holes in the domain. And the third one is, it could be simply connected or multiply connected. The important thing is the domain is infinite domain. Now, the choice of these potentials gamma and psi, they are different for different kinds of domain, the general choice of this potential. Okay. Now, for instance, I won't give you the detail how to get these potential, how to arrive at these equations. If you remember, at the beginning of this week, I gave you two references. One is one reference is by Mushkilesvili, if you go through that reference, you will get all the details how to arrive at these potentials. Okay, if the domain is a finite simply connected domain, then what happens? It is very similar to phi. We can have a polynomial assumptions like this: a state power series expression, though gamma is a polynomial, psi is a polynomial, a and b are the associated constants, and then those constants need to be determined. These are the general form, but it does not mean that we have to take the, if you look at this, it is a summation over infinity. So, it does not mean that we have to take we have to take infinite number of terms. We have to take a finite number of terms in these power series. Okay, this is for this domain. If it is multiply connected domain, then what happens? Then your potentials are this, and look at this Fk is essentially this Fk. First of all, there are two things. One is this summation when k is equal to 1 to n, this summation is essentially your how many loops you have, how many these such holes you have. For instance, in the given figure you have just three holes, so here k will be 1 to 3. Now, and what is Fk? Fk is the same for now each hole. If you have some boundary conditions, for instance, if you at this hole you have some forces specified here. Okay, so we know what are the traction at the boundary at this surface, at the internal loop, this loop. Now that traction can be converted into force. Just now we saw that force is equal to integration of this traction ds over this, now it is a closed integration, the closed integration. So, this will be Fk. So, Fk is the force on this. Similarly, if you have several, depending on how many loops you have, these are the forces in different loop. So, this first term is for this multiply connected because of these holes. Okay. Now, the second term is very same as the previous one, the simply connected case. Second term is written in terms of gamma z and psi z, where gamma z and psi z are the same as you can have the power series representation of gamma z and psi z for this part. Okay. So, in this case, the additional part is only the first one. Okay. Now, if the domain is infinite, this one now is a very general expression, the infinite domain, and also you have some it is a multiply connected domain. So, this part remains same in the previous one, this will be the same as the previous one. This is because of these internal loops you have, the holes in the domain you have, and m is the total number of hole, and this is the summation over the entire into the number of holes, and Fk is the forces specified on the loop. Now, gamma star, then the third part, gamma double star and psi double star as the same as at this expression. This is also written in terms of power series. Okay. Now, but look at, please look at one thing. One thing is very important here. If you look at the expression of this is written in terms of z to the power n, whereas in this case it is written z to the power minus n. Okay. So, it is essentially 1 by z, 1 by z square and so on. Okay. Now, and these are the stress values that is specified at the at the boundary. The infinity means at the infinite boundary what are the stress you have. For instance, you can have say normal stress here. If this is normal stress, this is normal stress, and these are the normal stress, these are sigma y infinity, this one. Similarly, you can have sigma x here, these are all sigma x. This is sigma x infinity. It means that at the infinite, if you fix this as boundary at infinity, then what is the stress on that? Similarly, sigma tau xy or sigma xy is essentially if you have some stress like this, these are the stresses, and these are the stresses at this. So, this is sigma xy infinity or tau xy infinity. it's the same thing. So, this is the expression of gamma z and psi z. Now, once we have the general expression of gamma z and psi z, it does not mean that we have to take this expression because entire expression, because it is a essentially infinite series. We have to take a finite number of terms depending on the equations and depending on the boundary conditions specified, depending on the information that we have about the problem. Okay. So, we have seen three different cases, and what are those three, what are the possible or the general these potential general form of these potentials for three different cases. Now, if you go through any book, there are many examples are given, and all the examples you can put either of this, any one of these three such cases, and you choose gamma z and phi z accordingly. Once we choose the gamma z and phi z, next of the process is the same way that we demonstrated in the previous class. You write the constant in terms of their real and imaginary part, and then substitute gamma z and psi z in the stress equation, and then compare the real parts and compare the imaginary part. You get the expression for stresses in terms of constants, and then you have the boundary conditions, traction boundary conditions specified, find out those constants. Similarly, you substitute these potentials in the Navier's equation, and then compare the real part and imaginary part, get the expression of u and v you have in terms of constants, and then boundary conditions are specified, apply those boundary conditions to get those constants. Okay. The process is exactly same. Now, next let us take one example. This example, just I will give you the, I will tell you the steps we have discussed. I will tell you the final results of this example. Particularly these examples, the solution of this example we are discussing today, because that solution is very important, because from this solution we are going to make a very important point that we will be doing in the next class. Okay. Now, you see this this is essentially the very similar to this is the case, the third case. Okay. It's a multiply connected domain and there is infinite domain. So, these are the general form of the potential. Okay. So, the potential will have, so for this case we have the potential like this, right. So, this gamma double star and psi star z is essentially this. Okay. Now, once we have that, then you see what in this example what information we have. You recall that this is the way, this is the expression for stress in terms of this potential, and if you use the polar coordinate system, this is the expression of different stress component in terms of the potential. Okay. So, this is essentially this part, if you this part is essentially the same as this part. Okay. So, this essentially become this into 2y theta, additional 2y theta. Okay. Now, so if you do that, now what information we have about this problem? Now, you see in this problem what we have is at this boundary, your sigma RR at this boundary, what we have is here you look at what is the condition we have, sigma R plus sigma R at R is equal to A, that is equal to 0, and sigma RR and sigma R theta at R is equal to A, that is also equal to 0. So, if we substitute this condition here in this expression, and anyway on this boundary sigma theta is not specified. So, if we substitute that expression in this here, in this expression, and then write this entire thing in terms of entire thing in terms of this potential, and the potential substitute the expression of this potential into this equation, and then we make them 0. They make them 0 because it is 0 in both the cases, it is 0, right. In both the cases it is 0 in this example. In both the cases it is 0. So, entire expression of stress will be 0. So, here this part will be 0. So, if we substitute that this entire thing equal to 0, then what we have is we have the final expression is this. Okay. This is the final expression. You can have these for a given problem. This may be some value, or you may have there is no stresses at the no stresses at that infinite that fictitious boundary at the infinity. So this part will be 0. Now once we have the, please I will just repeat once again this step. This step is very straight. This step is what? This step is you have the problem like this, and then you have at the infinite, at this boundary you have some stresses, sigma x, sorry, this is sigma x infinity, sigma y infinity, and so on. Now at the, if this is A, so at this boundary your stress is 0, sigma r is equal to 0 and sigma r and sigma r theta is equal to 0 at r is equal to A. Now you have an expression of sigma theta theta minus sigma r, then plus 2I sigma r theta is equal to something into your 2I theta, right. And this something, this is written in terms of the potential gamma z and psi z. What is now, this part is 0, this part is 0 at this boundary. If you satisfy this equation at this boundary, this step is 0, and substitute this potential, the expression of potential just now we discussed here, then you just slightly rearrange it and get this expression, entire expression. Okay. Now once we have the next entire expression, then the rest of the thing is we have to compare the similar term, either the real term, or then we compare the what is the in this case if you compare it to our ni theta term. If we compare it to your ni theta term, so then what happens, or in it to your 2I theta term, here you have 2I theta term. If you compare those terms, then what you have is you have expression for A1, B1, and all other expressions are like this. Okay. Now this is important. Yes. Now how do we get it? You just look at this expression, and if we compare whatever we have 2I theta term here, and whatever you have, whatever 2I, it your 2I theta term here, their coefficient should be same, and if you compare these coefficients, then you get this expression of A1, B1, then A2, all other AN will be 0 if it is greater than 2, and all other BN will be 0 if it is greater than 4. So essentially, even if you started with a infinite series, essentially what we have a finite number of term for the given problem. If you apply the conditions for the given problem, then you have a finite number of term. But remember, if the problem is slightly different, in the sense, if this is the internal, this is the hole, but suppose this hole is not the stress free hole, so you have some forces, you have some pressure here. This of that pressure is P. Then you may not get this equation, because this equation you arrived by substituting that boundary condition. In that case, that force, that stress will be, you have to write that in terms of the traction that we discussed, and substitute that traction value here, and you will get a slightly different form. And then if you again do the same exercise, compare the term by term and get the expression for these constants. Okay. Now with this, what is important for now is, now once we have this constant, plus look at, once we have this constant, then we have the potentials. Okay. In these potentials, what are the unknowns? The unknown variables are only these are the unknown variables. Okay. Now we know what are the boundary conditions we have. Substitute that boundary conditions, get these unknown variables. Once we have the unknown variables, we have the potential. Substitute that potential in the stress equation, and at any given point we can compute the stress field. Okay. Next what we do is this example particularly we are discussing. There are many examples given in the book in order to because of the restriction in time that we have. Here we cannot do many exercise problems, many example problems, and demonstrate all these expressions that we derive through some example. This is not possible. But here the purpose has been to let you know what are those, what are the concept, what are these equations, and how in a general way you can use these equations to, if you want to solve any problem in elasticity using complex variable method. Now please convince yourself by by applying these concepts, these equations that we derived in this week, and try to solve some examples yourself, and there are some examples given in the book. Until and unless we really implement these equations and solve them, things may not be clear. Okay, particularly this example we discussed, because from this example we want to solve this example. You have an infinite, you take a domain and then this domain as an elliptical hole, okay, and this is subjected to some forces like this, okay, some forces like this. So, we use the solution of this equation. The solution of this equation, just now we derived the solution of this equation is this. This is the solution of this equation. Now, we use the solution of this equation to get the solution of this. So, this is elliptical hole. So, suppose this is 2b and this is 2a, and this solution, from this solution we will make a very important point. The point is so important that that is essentially a starting point of a different branch in mechanics. Just an example, this problem opens a door or provokes you to think some important concepts, some important thing that will open a door, or that will open a door to a new branch of mechanics that we'll discuss tomorrow, next class. Okay, with this, so I stop today. So, next class will be complex variable solution of elasticity problems using conformal mapping. The conformal mapping, because this example we cannot, it will be tedious to apply the boundary conditions here, but we define a map from this circle to this ellipse, and that maps will be the conformal map that we discussed in one of the classes this week. So, use that map to get the solution of this equation. Okay. So, next class will be the solution of boundary value problems in elasticity using conformal mapping. With this, I stop today. See you in the next class. Thank you.